Alright, so this is Griffiths Electrodynamics, problem 2.34. We are going to find the energy stored in a uniformly charged solid sphere of radius big R and charge little q. We're going to do it in 3 different ways. So, first we're going to use equation 2.43. So that looks like this. Okay, and this detail in Griffiths' book is the differential volume, right? So we're integrating over volume. Okay, so back in problem 2.21, we solved for the potential inside this sphere, and that's what we're going to use for this. Because we're integrating over the charge density, there's no charge density outside the sphere, so we're only integrating on the inside of the sphere. And rather than put us through all of that again, I'm just going to write out basically what we got. So this is the inside of the sphere. Okay. I believe we have a video of the whole, oops, this is a big R, the whole derivation of that, so if you don't feel comfortable with it, review the video. Alright, I don't know if I factored out this 2 big R last time or not, I don't remember. But yeah, the final answer can be written like this. Okay. Alright, now we need to know, so what is rho? Because Griffiths here in this problem, we're looking at a total charge of Q. So total charge of Q and radius big R. Alright, so rho is just the charge over the volume. Since it's a uniform charge, right? So the total charge is little q, and the volume of a sphere is 4/3 pi. Alright, I'm going to flip the 3 up to the top. 4/3 pi r cubed, and this is the big R, the radius here. Alright, so now we have our 2 pieces, and we'll just do our integration. And yes, I should note that this is all part A. Alright, so we have this factor of 1/2 out front. We're going to be integrating. Alright, none of this depends on the angles in the problem, right? Radially symmetric. So I'm going to skip the angular integration because in all the cases like that, right, you get just a factor of 4 pi, right? So when you look at the Jacobian or whatever, you know, the sine of theta, d theta, d phi, you get 4 pi. So I'm just going to integrate from 0 to big R, and I'm only going to do the radial integration. Okay, so now, so I kind of skipped ahead and did a little bit of this volume right here, but now we need our rho, 3q 4 pi r cubed, and then we have our v here, q over 4 pi epsilon naught 1 over 2 big R, 3 minus r squared over big R squared. Okay, and then for our radial integration, we still have a factor of r squared from our Jacobian, so r squared dr. Alright, so let's try and bring some of these constants out front. Right off the bat, I'm going to divide this 4 pi by 2 and have a 2 pi here. Looks like we have 3 over 8. If we look at this 3/4 and this 1/2 out here. Oh, there's another 4. Oh boy. Okay, this is just an intermediate step anyway. So 3/4, 4, 2. We have a q squared up top. These two guys. We have now pi squared on the bottom from these two. And then we have 1 epsilon naught. And now we just have this r cubed and this r. So I really hope I didn't miss anything in there. But I think that's our constants. And now for our integral, we have this term right here, which is multiplied by r squared. So we have a 3r squared minus r to the 4th over big R squared dr, right? So just multiply this into there. Okay. So let's see what we can simplify here. So one of these pi's will divide out, and then we have this what would be 6 over 32, so a 3 over 16 from those. And then so we have our q squared over 1 pi that's left, 1 epsilon naught, and then r to the 4th. Okay, now we have this integral. So so we have an r cubed, so r third over r to the 3rd power divided by 3, but there's this 3 here that divides out. So we have an r cubed from this term, minus r to the 5th over 5 r squared. And then we are evaluating this from 0 to big R. Over 16 q squared pi epsilon naught r to the 4th. All right, so here we have an r cubed from here once we evaluate this at these two boundaries. And then we'll have an r to the 5th over 5 r squared. Okay. So we're looking pretty good. All right, so I'm gonna go ahead and just write this in real quick. So I'm gonna multiply this and divide it by r squared, so we get the same. How about 5r squared? So I'll multiply the top by 5 and the bottom by 5. Multiply the bottom by r squared, and this will turn to an r to the 5th. Multiply the top by r squared as well. All right, so now we have an easy subtraction here, and this piece, we put it up here in this little corner box. 5 minus 1, so 4 over 5r squared times r to the 5th, right? We can simplify that down. So we'll divide out by r squared and make this an r to the 3rd. This is really messy, all right, but we'll write it again down here because that's a big mess. So 3 over 16 q squared pi epsilon naught. All right, so this was, what was it again? It was an r cubed on the top. All right, r cubed over r to the 4th. And then we have this 4/5 out here. All right, so I think I have all the pieces here. You can rewind the video if it gets too messy, and hopefully I've at least said it clearly. So I'm gonna divide the 4 down, okay? Divide by 4 top and bottom. And we're going to kill the r third on the top, and we just have 1 power of r here on the bottom. So here's our final answer. I'm going to have a 3/5, and the reason I didn't put this 4 in here is so we can have our 4 pi epsilon naught factor that we love so much. Okay, so we have 3/5, we have the 4 pi epsilon naught, we have the q squared, and now we just have 1 power of r on the bottom. All right, so this is important because this is only part A, as long as this is, right? So we still have to calculate this 2 other ways, and this is the answer that we're going to be comparing to. All right, so for part B, we're going to be using the equation 2.45. Write that here at the top. So we have an epsilon naught over 2, and then an integral of the electric field squared, and then d tau, which we use for our differential volume element. And we have to remember that this is over all space. Okay, we can see that right from the equation in the book, equation 2.45. And okay, so what we need to know is the strength of the electric field inside this solid sphere and outside it. And when we use Gauss's law, like we've done in these previous problems, right? Whatever, it's quick, let's just do it real quick. So remember Gauss's law, we know the direction of the electric field, we're just solving for its magnitude. Using, I'll write it down here. Right, the surface integral. Charge enclosed in our surface over epsilon naught. Okay. So again, review the Gauss's law videos, but here's the magnitude we're solving for. The area of the surface of our Gaussian surface. And then inside, the charge enclosed will be q over epsilon naught times the ratio of r cubed to big R cubed. All right. So inside, we have a bring 1 over, well, q 4 pi epsilon naught. Okay, and then we just have 1 power of little r on top and 3 powers of big R on the bottom. All right, for outside, we get but this time all the charge is enclosed. All right. This, so outside q, right, 4 pi epsilon naught, and there's drops off as 1 over r squared. All right, so a quick review of Gauss's law. All right, but these are the electric field strengths that we're going to be putting into this equation. All right, so we have 2 integrals to do. One is, and again, I'm just going to do the radial integrals. We just get a factor of 4 pi from the angular part. So again, I'll put that out here at the beginning of the integral. So the inside one is 0 to big R. So we go and we look up what's the E on the inside, and then we have to square it. So Q R 4 pi epsilon naught big R cubed squared, and then we have a factor of R squared from our Jacobian. All right, and now we're going to do the same integral, but for for the outside, from r out to infinity. Again, the angular part just gives us 4 pi, and now we just need to use our other electric field for the outside. Q over 4 pi epsilon naught for r squared, quantity squared, and now we'll have an r squared dr as well. All right, so here's our two integrals that we need to do. Let's see if we can bring constants out front, so forth. All right, so if we look at our 4 pi epsilon naught, we have that, and here we have a 4 pi epsilon naught squared on the bottom, so we'll end up with our 1 over 4 pi epsilon naught, just 1 power left, right? And we'll get rid of this and this in each integral. All right, there's also a q squared in each integral that we'll factor out, and a 2 from out here. Okay, and okay, I'm going to go ahead and write out the integrals now. So the top one, we still have this 1 over big R cubed, and we're integrating from 0 to big R, and inside we have 4 powers of little r, so r to the, wait, no, 6, because there's 2 here plus 2, okay. R to the 6th dr. Now we'll write out our second integral here, which starts at right, we're integrating out, so big R out to infinity. Okay, and so all of this we factored out. Okay, so now this time we had this r squared, so r to the 4th on the bottom and an r squared on top, which leaves us only r squared on the bottom, or an r to the minus 2. Okay. So, starting to run out of paper here. We'll grab some more. 1 over 4 pi epsilon naught q squared over 2. Now we look at our first integral here. Make sure I did this right, because, yeah, I hope I did. Nope, I did not do it right. I don't know what I was thinking. Somehow my mind put an extra 2 in there. Why did I cross this out? Right? This is a 4. Right? There's only 1 power squared. Right? Okay. Again, my at least one mistake per video. So here we go. 1 over r cubed, and now we have an r to the 5th over 5, and evaluated from 0 to big R, and plus, okay, this is going to be an r to the minus 1 over minus 1, which is just a minus 1 over r, and evaluated from big R to infinity. Okay. Okay. So we'll leave our 1 over 4 pi epsilon naught out here. Q squared over 2. This will give us a, what will this give us? So on the top we have an r to the 5th, and on the bottom we have a 5r cubed. So big R to the 5, or 5r cubed. All right. And then once we take this minus sign, we'll take the minus sign out and flip this, right? So we have a plus 1 over r and then minus 1 over infinity, because this is 0. All right, let's see if this works out. We'll look at the factor in here again. So we have an r squared, or r cubed over 5, or let's see, let's put this, let me double check this, because these don't even have the same units. Can we make any more mistakes here? Did I make another mistake? Oh, honestly. This is a 6. Alright. Okay, because we had a 3 squared. This square just gave me so much trouble. Okay, so here's the 6 down here. Alright. Maybe someday I'll go put annotations in the videos and so if you don't catch my mistake as you go, I can make a note of it or something. Alright. Gee whiz. Alright. 4 pi epsilon naught q squared, and I'm gonna go ahead and factor the r out on the bottom, right? So r to the 5th divided by r to the 6th, we have 1 power of r on the bottom. Take that out. Alright. So we have a 1/5 plus 1, oh, and I forgot the 2. Wow. Okay, plus, so 1/5 plus 1. Okay, I think this is working out, okay? Because, so we have a 6/5 on the top, or this is equal to 6 over 5 right here, this term right here, divided by 2, okay? So we'll get a 3/5, right? So a 3/5 from this 2 and this 6/5. Then we have our 1 over 4 pi epsilon naught. Then we have our q squared over r. Alright, it's just a miracle we think caught our mistakes. And looky here. Here's the answer we got from part A. 3/5, 1 over 4 pi epsilon naught, q squared over r. So we're good on part B. So there's part A and part B, and we got the same answer on both. Alright, so now we're on to part C. And yeah, if we've had integration troubles on the past 2 parts, we're sure going to have them on this one, because we have, this is equation 2.44, by the way. This is before we take our volume integral out to infinity, and we end up with equation 2.45 over all space. So this is not over all space, it's over some volume. So here's our volume integral. And the surface integral. Again, this is the part that goes to 0 when we take our integral over all space. Okay. So we are going to assume, Griffiths says, take a spherical volume of radius A. So we'll assume there's some radius A, and it's big enough to enclose all the charge. So A is larger than big R. Now we will go ahead and let's break this into pieces and do our volume integral first. Okay. So this is, and again, because A is larger than big R, lucky us, we get to split this into 2 integrals as well. So, fun times. Yeah, so there will be one that goes out to R, and for this we need the electric field on the inside, right? And again, there's a 4 pi out here because I'm only doing the radial part, so we get a factor 4 pi from the angular part of this integral. q little r, just a linearly increasing field. This is squared. We have our r squared dr. Okay, this is just the piece of the volume integral that we're integrating the electric field only on the inside of the sphere. So now we'll have a similar integral from r, but this time we're not going out to infinity, we're going out to a. Okay? And for this, we'll need the field outside, so 1 over 4 pi epsilon naught, and a q over little r squared. This whole quantity is squared. We have an r squared and a dr. All right. So again, we're just barely getting started with this problem. We're only doing this front integral right here. All right. So again, this is our volume integral over just the volume enclosed by a sphere of radius little a. And we'll start bringing out our constants. There's a 4 pi from these two factors. 1 over 4 pi epsilon naught. Well, let's put the q in there too. And this is squared. Then we have 0 to big R. So here we have, let me see if I can do this right this time. So there's just an r squared inside and an r squared outside. So that's an r to the 4th over big R. And this time, hopefully I learned my lesson. This 3 squared, there's a 6 on the bottom. Okay. Big R out to our radius A. And what have we here? We have the same thing we did before, which is an r to the minus 2. All right, so 2 powers on the bottom are squared, so that's 4 powers on the bottom and 2 powers on top. All right. And it's a very similar situation to what we did before, except this time we don't have infinity right here, right? So let's see if we can do this. I'm lazy, I'm just gonna leave this 4 pi epsilon naught. Okay. This is out front, and now when we do this integral, we have, again, this limit 0, and anyway, so this whole term will be 0, right? R to the 4th is 0, so, or 5th, right? So we have a big R that we're raising it to the 5th, and divide by 5, big R to the 6th. So that takes care of this term here. Now the other one's a little tricky. Again, for in here, we'll get a minus r to the minus 1 when we integrate. And then we'll take the minus sign out and flip this. So we have a plus 1 over r. And last time we had a 1 over infinity here. But this time our limit of integration is a. Okay? And Griffiths says, like, what happens as a goes to infinity? Well, this integral will become, you know, the one we did last time where we're integrating over all space. So this term will go to 0 as a goes to infinity. And then all we need to do is answer this, or figure out this integral to answer the problem, which is what we did in part B. Where did all right, so that takes care of this integral. So what we were looking at was the total energy of this charge configuration was this integral, but there's also this surface integral. So now let's do this surface integral. It's not as bad as it looks. So we have a couple of tricks we can use. All right, so I'm going to put this volume integral off to the side for now. Okay, so again, this is a surface which is a sphere of radius A, which is larger than big R, so we're enclosing all of the charge. And since it's a radially symmetric situation and everything, basically, and we're using a radially symmetric surface, basically, because of symmetry, this V is going to be constant over the whole surface of the sphere. All right, so what is V? Let's go ahead and write it out. So the charge on the whole sphere is Q, and we have 4 pi epsilon naught, and downstairs, usually there's an R there when we, it's the potential of a point charge or this sphere, right? But we're out at a surface of R equals A, so I'm just going to write R equals A down by this S. So V is a constant over this surface, and this is the value of it. All right, so hey, we can actually bring V outside the integral. So I'm going to actually write this constant value for V, and then we have a surface integral of E dA. And where have we seen this before? This is the one that we always solve for Gauss's law, right? Except instead of setting it equal to the charge and whatnot, on the right-hand side, we'll just look at this. So remember, whenever we do Gauss's law, and we're in the symmetric situation and all of that, we always have an E and a 4 pi, and usually it's an R squared right here. But again, we're at this surface where R equals A. So a 4 pi A squared. All right? So this integral, which is this integral right here, so I'm going to put an equal sign right here. This integral here, which is just the surface integral, which is part of the bigger situation, right? Just the surface integral is equal to this, and then this part is equal to this. So we can divide out the 4 pi and one of the A's. We have a Q. Right, we're dividing out the 4 pi. There's one A on top, there's an epsilon naught, and there's an E. No, there's an E on top. Okay. Okay, I think I did that right. All right. Well, this right-hand side is looking even more like Gauss's law now, huh? Because we have a Q over epsilon naught. But, we are, all right, so now what we're going to do is just plug in our E. All right, and what is E? I'll put this down in a box so we don't get confused. Well, out at R equals A, E is just, it's the field of a point charge again, Q over 4 pi epsilon naught A squared. Okay, so putting this together, we've just, in this kind of piecemeal fashion, we've put together what this integral is. So I'll write out the original integral. And you may want to be more formal about it, I don't know. But okay. So here's the original integral, and we just had this QA over epsilon naught multiplied by this E. So Q over 4 pi epsilon naught A squared. All right. And let's just bring up a couple of things together. So we have a Q squared on top. Dividing by A, we have one power of A on the bottom. We have a 4 pi, and then we have 2 powers of epsilon naught. So this is Q squared over 4 pi epsilon naught squared times A. All right, so this is just the surface integral. We have to combine it with this volume integral that we've done, and we multiply the whole shebang by epsilon naught over 2, and that will give us the work. So let's go ahead and do that. We have our factor of epsilon naught over 2. Now we will put in this, which was the volume integral, and add on the surface integral that we did. So, time to simplify this a little bit maybe. So this is our Q. Okay, wait a sec. Oh, another mistake. Seriously. All right. So I don't have a 4th power of Q here. I should not have done that. Okay. There's always mistakes. Okay. So we have a Q squared, right? Now there's only 1 power of 2 here. Q squared, not Q to the 4th. That would be crazy. And then there's 1 power of 4 pi. And 2 powers of epsilon naught, right? This one's still squared. No, there's no epsilon naught to divide out with it. And look, that also corresponds to our the surface integral that we did. So I'm going to go ahead and factor this out of the whole thing. Okay. I don't remember whether we did this part already, but one thing, right, this, if we go back and look at our volume integral, maybe we did this on another paper, I don't know, but this 5 can divide out with that 6. So similar to before, what do we get? We get a 6/5 with an R on the bottom for just this little piece right here. All right, so 6 over 5R. Then we had a minus 1 over A. Okay, so this is just the volume integral. Now we're going to, so here's a refresher. Here's our total energy. Here's the volume integral. Here's the surface integral. We just have to add the surface integral on. So now we add on this term right here. Well, we've already factored out a Q squared, a 4 pi epsilon naught squared. So we're just adding on a 1 over A. All right, well, this is looking good because what we've got now, if we use one more sheet of paper, I'll go ahead and divide out one of these epsilon naughts. So we have a 4, well, let's go 1 over 4 pi epsilon naught. Okay, we have a Q squared on the top, and 2 on the bottom. And now these 2A things cancel out. So we have a 6 over 5R. And basically divide by 3. And we have a 3/5, 3 over 5, our 1 over 4 pi epsilon naught. And then we have a Q squared over big R. Here's our final answer. And gee, if I can rustle my papers here and get back to previous answers that we had. Here's one of them, right? 3/5, 1 over 4 pi epsilon naught, Q squared over R. right? And if we go, this was from part A, I believe. We go find part B again. We've already compared the two and shown that the first two parts were equal, right? Well, anyway, wherever it went, we've just, we've got this answer for all three different parts. So we've shown three different ways that we can calculate the energy of this uniformly charged solid sphere of radius big R and little charge q. We've done our three ways, and in problem 2.35,